Welcome to the final presentations of the AI for Road Safety Challenge. We've organized this challenge together with Project Araste. Welcome, Govind and Amrumani, for joining us, and we're very proud to present the results that we've come up with over the last 10 weeks. For the people who are new here, who have never seen us before, we are Fruit.ai and we are the global AI for Good community. And we have started this community because we believe that to solve humanity's greatest challenges, we need to educate AI engineers at scale with an ethical and sustainable mindset. We do this by organizing AI for Good challenges. And how do we define an AI for Good challenge? That's basically if we can assign a problem towards one of the sustainable development goals. There's a data problem that we can solve with an AI solution. Then we have an AI for Good challenge. We organize challenges in the wildlife space, climate change, but also in healthcare and infrastructure, of which one is this challenge is also one, so better infrastructure. For today, we have three very nice presentations on insights on the Indian road safety. Over the last 10 weeks, we worked with 3 teams and 14 AI for Good engineers with a combined effort of around 12,000 hours of engineering work. With the goal of unveiling accident triggers. So uncovering patterns and signals through exploratory data analysis and machine learning from a collision avoidance dataset. So just to give you a brief idea of what the dataset was we're working with, within large cities in India, there were some collision avoidance systems located in public transport vehicles that would give up triggers or alarms whenever, for example, a person crossed the road or the driver was changing lanes without signals, collision signals that were added to a very large data set of over millions of data points. And it was up to the team members to find interesting patterns and maybe find some insights that no one has ever thought of before.
I think you all can see my screen. So we are Team One Punch, the first team. Our team is Akash, which is me, Timothy, who's also going to speak later. Then we have Ritin, Jonas, and Sharadi, who are also part of all the team activities that we have been formed of. So initially, I'm just going to go through what we had showcased in the midterm, just to have a quick recap. Dorian already had the data set and gave the initial goal. I had that slide, but I'm going to skip over that. So initially, or during the midterm, what we showcased is that with the given data set, what we decided finding our initial EDA was to go with speed, location, and also as the most important factors. And we also got some weather data from external Telangana government dataset, which Ritin had accumulated, which we incorporated into our dataset apart from the given IRAS dataset. And another thing which we also were able to do is reverse code the location, which was the longitude and latitude points, to actual hotspots in and around the Hyderabad, Telangana area, so that we can get much better insights. And just a recap from the midterm was one of the graphs which we were able to showcase is the mean average speed during regular weather, which was basically low wind speed, low rain, and also decent temperatures for drivers to drive. Whereas comparing that to extreme weather, which was high wind speed, high rainfall, and really hot temperatures. So this was just at the midterm, and after that, or the feedback which we got from during the midterm presentation from the IRAS team was that we should now look into how these individual factors correlate with each other, and what insights we can get, or extreme insights which we could get. So that's what we started, and the first one which we looked at was the location and the alerts. So for this, what we did, actually, I have something to showcase, like an interactive video. Yeah. So first of all, what we considered hotspot is where the number of data points, because we had 2 million data points, so we had to kind of trim them down so that we can run our algorithms much more efficiently. So what we considered an hotspot is that if the number of data points was more than, for each alert, more than 1,000, and then we kind of accumulated that, and we used something called Folium, which was an interactive map. This is just a screenshot. I'm gonna hopefully this, yeah. So this is like an interactive map which we could generate, and this is based on each alert. The first point is that we ignored the LDW alerts because we generated them initially because first of all um, there were a lot of data points just for LDW, and this I had talked during also my midterm that we had decided to because it was a misclassification or imbalanced data set. So we had decided to first of all reduce the LDW alerts. But then even if we looked at the LDW alerts, they were kind of noisy, and we thought they didn't give us enough insights or relevant enough. So we looked at the other three factors, which was HMW, the pedestrian collision warning, the PCW, and the FCW. So coming to HMW, what we realized, building this map, which is from Folium. So just another insight on how we got this interactive map. It's a bit laggy because it's taking a lot of the processing, and it's so if you can also zoom in, find the exact data points, and these are alerts per 1,000 data points. So they are just, yeah, divided by 1,000, you can say that. And one of our teammates employed an R3 algorithm to index nearby data points and efficiently, so that we can speed up the process. Because also this I mentioned during a midterm that we were facing an issue of computational efficiency because there were 2 million data points and we could only work on 100 million. So that's how we decided to speed up our computation efficiency. Now, what you see, this is for HMW, is basically it's mostly coordinated along the highways, and also this is like the state highways, which makes sense because headway monitoring is generally when it would occur mostly along the highways because it gets triggers when the distance to the other vehicle in the same lane is less than the safe distance, predefined safe distance. So that kind of was the insight which we kind of expected. Oh, sorry, oh, sorry, that was FCW which I was talking about, and yeah, I think my lab. I'm just going to show the screenshots. And moving on to PCW, which was the pedestrian collision warning systems. So what we saw, I think this should be working. Oh, this is also gonna. Yeah, it's just lagging. Hmm. Sorry guys. Oops. Yeah, I'm just going to continue with the screenshot. Yeah, so for PCW, what we saw that the alerts were concentrated near the bus stands and urban areas, which again makes sense because PCW, I don't think you would find many pedestrians on the highways or, really broad roads. So they will be near the where there are hotspots, especially near the bus stands. So this, what you see right here, this concentrated area is, I wanted to show it in the interactive map, but this is actually two major bus stands in the, yeah, you can also there's like a train station here, so that's also a really concentrated area. So that was one correlating factors that we looked into, which was location plus alerts, and we got the insights using some algorithms, and also as I mentioned, using an interactive map API, which was Folium, which as you can see is a lot heavy, but that's why, but if needed for the Arasta thing, we can upload it to some server, and yeah, you guys can also have a look at it. Moving on to the other factor which we looked at is what we looked at, it was location plus speed. uh I'm not sure if Ritin is still there in the call. Otherwise, yeah, I can also speak about it. Yeah, so Ritin, one of our colleagues, he used something called Kepler.gi, and I'm just going to play this video. You can see, but I'm also going to talk through it. So what we wanted to do is experiment the visualizing the location coordinates with speed. and we use something called Kepler.gl, or he used it basically. And yeah, it's basically a scalable tool for visualizing millions of points. So in this, what you generally see on the left side is, sorry, on the right side, you have like a legend, which you can see basically the speed heat map or colorized. And yeah, what in the video, what we're trying to show is that, again, uh, which would be obvious, is that around the actual Hyderabad or the urban inner city area, the speeds are quite less. Whereas if you go on like something like a highway, the speeds kind of increase. And this was kind of obvious, but also this such kind of visualization can be used basically by the IRASTA team or somewhere to monitor speed restrictions, or have better, even by the road safety organizations in India or around Telangana, Hyderabad area, so that they can have these speed restrictions and kind of prevent these alerts, and also reduce incidents or risk accidents for. And this is also related, which in the video, as you can see. So we took all the 2 million data points in this, and this has all the 4 alerts, not just the 3 alerts. And next up we have Timothy, who's gonna talk about, yeah, I think the rest of the video is pretty similar. Like, we have something for each alert, and yeah, it's basically just the speed data points, but the visualization was really cool, what we found, and that's what we wanted to show during this presentation. Moving to the next slide, if I can hopefully close this. Yeah. Timothy, are you there?
Yeah, I'm here.
Yeah, if you can continue. Yeah.
Right. So yeah, we decided also to look at the sequences of alerts. So how often does one alert lead to another alert within a short time frame? And we chose a time frame of 5 seconds. So I guess if you go to the next slide, we created a heat map to visualize these sequences. And what surprises us is that 25% of headway monitoring warnings lead to another alert um, within 5 seconds, meaning that a quarter of the time there's another warning after that one. But about 15% of the time, it's actually another headway monitoring warning, meaning that the driver is probably not just simply not keeping a safe distance with the vehicle in front. And other interesting insight is that, of course, lane departure warnings are the most common type of alerts. So they often lead to other alerts as well. But what is surprising is that so 3% of the time, which you can think is pretty low, they lead to a forward collision warning. But as there's a tremendous amount of lane departure warnings, that's actually a quite high percentage. That 3% of the time, that leads to a forward collision warning. And forward collision warnings themselves are actually followed by lane departure warnings quite often as well, meaning that a driver is probably switching lanes after receiving this warning to avoid a collision. And another interesting thing is that hard brake warnings are pretty rare, which is surprising because you would expect hard brake warnings after something like a forward collision warning. But this is something I'll come back to in my next slide. If you go to the next slide, yeah. So we also looked at the speed at which these sequences happen. And of course, when for lane departure warnings, the speeds are much higher because lane departure warnings tend to happen on the highway. But we can see that the standard deviation for forward collision warnings, so meaning that the average speed at which they happen is quite high, meaning that forward collision warnings tend to happen not only on the highway, but also at lower speeds when there's pedestrian crossing warnings, for example. And the thing I was mentioning about the hard brake warnings is that actually in the data, all the alerts preceding a hard brake warning have a speed of 0, which might be an anomaly in the data. which would explain why we don't find a lot of hard brake warnings after forward collision warnings, for example. And that's about it for the sequences. I'll hand it back to Akash.
Akash, you're on mute.
Yeah, sorry. Kind of did it. Yeah, so thanks, Timothy. So yeah, that's what we mostly looked at after midterm. Yeah, we kind of didn't after the midterm, the first 2 weeks were really hard because yeah, everyone had some personal reasons, and I could definitely understand. But at least we have some interesting insights for correlating the three important factors which we think are of the data set. And we would have liked to build some sequence model using or some statistical model to predict a risk score using I think FCW as the risk score, which was suggested to us during the midterm as well. But yeah, we weren't able to, or we weren't able to put in the work together to find that or develop that statistical model. So I think the final insights which we have, okay, I cannot. Yeah, those, I think those, yeah, there's one slide missing, but probably, yeah, this is the end of the presentation. And yeah, if anyone from our Rasta team has any other questions.
All right, thank you guys.
Yeah, it's really good, Timothy and Akash. I really found it interesting. The couple of things which are, as far as I'm concerned, is that the weather pattern and the heat map that you showed on the speed, that the Kepler, it's pretty good. And also, Tim, you talked about the FCW, yeah, that the 5-second thing is very interesting. We've also been thinking about it. We have done some work on that. So I think the FCW occurs, very less number of times, but it's a much more serious condition. It's usually followed by LDW or HMW. So these are good insights. Yeah. So I think, Anbu, do you want to add anything?
No, you captured everything well, good. Really, I'm really happy to see that the team has done very well. And
Absolutely.
the use of Kepler and Folium,
Mapping.
yeah, and especially the correlation plots, right? That's by Timothy, right? Very good. Yeah.
Very well done.
Good.
Very well done. Very impressive.
Yeah.
Thank you.
So, Akash, you also mentioned about the constraint of using, not much, 2 million data points versus 200K or something, right?
Yeah.
So what could be done to scale this, whatever you have done, because this is just a sample data, right? Imagine floating in a larger ocean of data. What would be your
Yeah, I think like initially,
any recommendations from you will be helpful. Yeah,
I think initially, at least during till the midterm, we were using only 120,000 data points or 120K. But then, especially Timothy, he decided like we should try some efficiency algorithm for the Folian, using the Folian API for the maps at least. But apart from that, yeah, I think if we could get better resources, that's the only way that we can.
okay, good. Because we will have the larger volume of data, and
much more, I
thought
think.
you would have.
Yeah.
Your recommendations will be helpful. Thank you. Not a problem. Thank you. Good job. Great.
Thanks.
Nice. Thank you, Team One. Thanks for the presentation. Great work. I think we can head on to the second team then. Who is going to present there?
Hey, hi, Dorian.
Hey.
Hello, all. I'll present it. Is my screen available?
Yes.
Yes, now. Yeah.
Okay. Yeah. Dhruvan, you can start the presentation.
All right. Thanks, Prasad. Thank you, Dorian. Hi, everyone. So this is Team 2. We'll go over the final presentation. Prasad, if you could move to the next slide. Obviously, the problem statement we've discussed, and Dorian, you presented it. There is a large data set provided by the IRASTE team, and the teams participating in the challenge are looking to leverage that data to come up with interesting patterns and insights out of that. Obviously, it's a very, very critical problem, and we've discussed that through our midterm presentation as well as the final presentation. So I'll just skip over it. Prasad, if you can go to the next one. Yeah, so basically in the of the team, one of the challenges we faced is post the midterm, a couple of team members again dropped off. So it was Prasad and me focusing on a bunch of things post our midterm presentation. Prasad, if you could go forward. Yeah. So just a quick recap on thoughts on the midterm. Basically, during the midterm presentation, what we've done is we've done a bunch of exploratory analysis, looked at the data through various cuts, looked at sort of vehicle level cuts, speed level cuts, tried to see what are the interesting patterns that are emerging, and using that we'd come up with three possible streams that we wanted to explore. So three hypotheses that we wanted to test. That was our final sort of take on the midterm, which sort of highlighted the path forward. The hypothesis that we looked at is basically, can we create a risk score for a driver or a vehicle based model based on historical data, based on looking at the vehicle data, the speed data, bringing environmental factors, etc. We've been able to do some work here. Then we were also looking at the data from a city level insight to see alert densities to come up with hotspots that can be identified along various routes or within a given city. We'll talk about some of the work we've done here. And the third area that we wanted to also pursue was to use FCW as a near miss indicator and then create a accidental risk model. This is a stream that, given the paucity of time and the team size, we were not able to make a lot of progress on. With that, let me move on to the next slide. So yes, so the first one we worked on. So our focus was majorly on building a demoable product using Streamlit app. So in terms of building a vehicle risk identification, we've used alert types. We've looked at various alert types using the severity of those alerts, and then correlating it with a little bit with the speed. We've tried to assign risk scores, and Prasad will talk through it a little bit more as he demos the dashboard that we've created. So then basically based on the alert severity, vehicle risk score, you get vehicle speed, you get a risk score that is normalized over time, and then you categorize the vehicle into low risk, medium risk, high risk, right? We've also integrated that dashboard with bringing in road types. So we've looked at the lat long provided from the alert and tried to reverse map it to the road that the vehicle was plowing on. We've not been able to incorporate that as much in the risk score, but in future, looking at the road type, a highway, city, etc., that could also sort of be a factor on the risk. And then we've also brought in some weather data, which could again be an additional parameter that could be incorporated in the score. Right now, the score is majorly focused on the speed and alert severity. With that, I'll sort of hand it over to Prasad to demo the dashboard.
Yeah, thanks, Dhruvan. Yeah, the dashboard that we have created, are you able to see this dashboard?
Yes. Yeah.
Okay. Yeah. Here basically a user can select a vehicle. Here you can see the list of vehicles, and when your user select the list of vehicle, and it will show the vehicle risk score that we have calculated, as Dhruvan mentioned, through this. Given the time and strength we have, we majorly focused on the hypothesis, and the data is just a plug and play. Like this is the hypothesis. You can provide any data that will give us these insights. So it will create a vehicle risk score and create a map view like this. Here you can see these data points, and it is distinguished based on the alert type. You can see it is a hard brake, and it is a LEW alert, and it shows when where the vehicle starts its journey and where it ended, and a basic alert alert count distribution here, and alert count over an interval of time. What is the count of alert when it is at night? You can see LEW is more at night time, and the scattered plot of speeds. Like, I mean, where these alerts are high, I mean, falls under the speed range. So you can see that heartbreak falls under at speed 0. It is obvious, like when it is a heartbreak, the speed is 0. So we can relate that. So we can have a quick view of the counts, I mean, alerts over the speed. And we can have a state level, district level, average speeds and max speeds. Why we have done this, using some APIs, I have created a speed limit for that particular location. But due to the lack of completeness, like I am able to get a few data points of for the speed limit of the particular area. So we can consider that as a risk. Like if a driver is not following that speed limit, we can, I mean, definitely add that to a risk score. So we can basically view, I mean, how the driver behaving at this alert. So at the CAS LDW, the average speed is 72, and max speed the driver maintained is 80. And we have added a few weather data also. So you can see the data here, average speed and max speed at this particular weather. And you can change the vehicle and it will automatically update it. So red means the vehicle is at high risk, and yellow means is at okay risk, and green means vehicle is good. I mean, the risk is not high. So this dashboard is basically, we can quickly view these insights, meaningful insights, and we can decide how, I mean, the vehicle is behaving and all. I mean, obviously the vehicle or the driver, we can assume that the vehicle, I mean, vehicle as a driver and all. So this is the vehicle risk analysis. And yeah, these are the, I mean, formula we have used to calculate, as driver asleep. For example, if the driver is not, I mean, aware and he is asleep, the risk score is high. We have considered the risk score from 1 to 5. So, I mean, if the severity is high, we given the risk score to 5, and the severity is low, something like LDW with the speed maintained at low to mean, the risk is 1. Risk score is 1. So that's how we calculated the risk score for a particular vehicle. We can incorporate some more insights to it, if the heartbreak is it highway or is it non-highways, and if FCW, what is the speed he maintained at FCW? I mean, how is it a crowded area or is it a public transports and all? So based on that, we can always, adjust this risk score, and we can even standardize this calculation. So this is how we calculated the vehicle risk score. And then we have worked on the, hotspot analysis also. So I'll quickly show that as well. So in the hotspot analysis, we can we plan to showcase using a city level, but due to you have seen that the maps are loading is of volume. So due to some computational, the Chrome crashes. So if we go with huge data and all, so I restricted the data to road level, so we can load the volume. Yeah. This is how it looks like when we selected NH44 and alert test CAS LDW. We have we have included 3 different types of maps. You can see this is shows the density of the alerts where the red region, and we can interpret it mathematically. I have used a clustered map also. There you can see a numbers. It will take some time. Okay, let's change the row type. Let's this. Yeah, here you can see in this area there are 521 alerts, and you can zoom in, like you can see how many alerts are there numerically. So in order to see how denser that spot is, how many alerts appear, occurring in that region. So you can zoom in and zoom out. These clusters will arrange automatically, and you can have a normal view as we have seen in road, vehicle level analysis. And there is a small data about it, where it is started and where it ended, and the speeds across an interval of time at night, how it is maintained the speed, and at morning, and interval of day on alerts, like how many alerts occurred at the interval of time. I mean, at afternoon, how many alerts of this particular type occurred. We can select a multiple alerts as well. Yeah, see, it changes accordingly. And yeah, usually speed versus count of alerts, at what ranges of speeds the alert are distributed, and basic view of alert count, and average speed maintained in that region, and obviously, weather data. And also, I forgot to tell you, we can even select the date ranges as well. So in the end date, I can have just up to 5th May. Yeah, so I can see the number of data points have been decreased since I have decreased the date range. Yeah, that feature I have made available in that vehicle risk analysis also. I think the memory usage is being. Yeah, here also you can always choose the date range. Okay, I think I have used almost the memory. Okay. Yeah, and dashboards will update accordingly. So that's what we have achieved so far. So instead of concentrating on gathering the data, we just applied our hypothesis on this data. So Dhruvin, do you have anything to add?
No, I think this is great. So the idea of both the dashboards are slightly different, right? The vehicle risk score is for a manager who's sort of managing fleets, wants to see how the vehicles are plowing, and from the data gather insights on which like vehicles slash drivers are having risky behaviors. Obviously, we focused right now only on alert and speed, but we know what roads the vehicle are plowing on, and that could be incorporated. The cluster mapping is for someone who's managing traffic, looking at infrastructure. So if you can go to that, I think the key factor here is we're looking at a road level analysis. So yeah, you can go to the heat map. So if someone is managing the airport approach road on Hyderabad, right, they can actually see which is the area where you're having a. And Prasad, if you can just take one alert, let's say HMW, which is a severe alert, they can just zoom in and see which locations you're seeing a lot of HMW warnings, right? And those, as they zoom in, will concentrate on certain spots, and they can see if that spot needs to be managed much better to avoid any collisions, etc. Obviously, airport roads are better managed, but the same can be applied to highways and stuff. So, Prasad, if you can maybe select a highway. Yeah, so NH44, right? So again, you can zoom in and see areas where you're seeing a lot of let's say concentration of alerts. That gives you locations where you need to be more focused, manage the traffic better, etc. So yeah, overall those were the two areas we had sort of dived deeper into and focused on. Yeah, that's about it from team 2.
Yeah, the dashboard is looking really good. Did you use a database for Streamlit to pull, or it was based out of Excel?
uh
It's based out of an Excel.
Okay.
that we have generated using some API calls and all. We have used visual crossing API for weather data and OSM street maps for getting the location information.
Okay. Okay. So you consolidated all the output results that you want to show in Excel, and Streamlist just uses the Excel and shows you different formats, right?
Yes. Data
Yeah.
is just a plug and play. That's what I have mentioned. Yeah,
Okay.
we have not much focused on calling the APIs and all. Since we have very little time and strength is also to only contributing it.
Yeah, the dashboard looking very good. I think that's the unique thing you guys have done in this group. Very nice.
Great work, guys.
I like the
Oh, sorry. Go ahead.
I like the vehicle risk score analysis that the team has thought through, right? Using some weightage of values, the team has come up with it, and this customizable dashboard is a good thought, right? But I see that this is still Folium, which is still because it's browser based. The number of data points that the team can or the dashboard can analyze is limited. But good job. I like that your thought that you have put on this. Considering it a product demo and coming from that angle. Nice work.
Thank you.
All right, thank you so much for the presentation, team 2. Even though with just the 2 of you, I think you managed to get some amazing results. So hats off to you guys. Very nice. And I think that brings us to the last presentation, team 3.
Hi, Dorian. Gabriela will basically share her screen. She has a presentation, and we can quickly start.
Yeah, give me a sec.
Perfect.
Okay.
Hello, guys. This is Team 3. I'm Dishant Vyas, and I'm a software developer. And my teammate is Gabriela. She'll give an introduction.
Yes, hello, everyone. So I'm an ML scientist, and yes, this is our team.
With the Team 1 and Team 2, we also had the struggle of finding people to work on the problem, but we have made some progress. And can you go to the next slide? So we already know the problem. It's about road accidents. It relates to public safety. It results in injuries, fatalities, and often economic losses as well. The problem relies on understanding the major cause of road accidents, and there can be more than one factor that leads to those road accidents. So the goal of the problem was to basically take a deeper dive into the data set provided by IRASTE, and then hopefully find some positive insights as to how to tackle the road safety, help in accident prevention, and also improve the infrastructure for the accidents. Next slide. One of the major struggles that we faced were basically integrating the additional data sets that we wanted to. We focused on getting the road information, which included the road, like the name, the pin code, and as well as the road type. And with the data set being so big, it was a little difficult. We were able to do it for most of the regions in Telangana, but it was not possible for other regions like Nagpur, which had over 400,000 alerts. And that was one of the struggles that we faced as well. The next slide, please.
Yes, okay. Now I can start with what is our solution. And our solution is very basic, to say so. We have 3 main steps. So what we wanted to do is visualize our data and also complement it with external data sources. So as the first step, we collected data. Of course, we had the project IRAST, but we also went out and looked for additional data sources. We are using Overture Maps data, And as Dishant was mentioning, we wanted to use some other data sets, but we had some constraints. Then we process our data, and this means we clean our data, and also we perform one important step, that's the spatial aggregation. And this is done because we have a lot of data and we need to see a way to make our calculations more efficient. So we will talk more in detail about it in a sec. And finally, we analyze and visualize our data. And we do this with an interactive dashboard. And for the presentation, the midterm presentation, we presented a volume map. But for this one, we researched some tools and we found this Kepler GL that the other teams have also used. And this is very good for analyzing dynamically our data, and it's also efficient, and it provides support for spatial aggregation visualization. So for the first step, the data sources that we used were first the project IRST data, of course, the alerts. Then we use Overture Maps Foundation. This is an open source data provider that would get all of the information from OpenStreetMaps, and it's available for many regions in the world. So it was available for our area of study, and that's why we use it. And we also wanted to use data related to the accidents, to the actual traffic accidents, but we did find that coming from the Open Government Data platform, but we face some constraints. The first one being that the data there is not updated, so at least not up to date, I would say. The last data source that we found was from 2019 or 2020, so it was not really that useful for us to compare or to integrate it with our alerts data. And the second constraint was that it was aggregated by city, sometimes by state, so it wasn't really providing like the actual coordinates, and we wanted that level of granularity. And then we also considered using roads information. This was coming from GeoPy, but this is related to what Ishan was mentioning before. It was very hard to get this type of information for the 1 million points that we have, over 1 million. And it's also because this GeoPy library, even if it allows us to kind of make requests to it, it's not a service, so it won't allow batch requests. So that's why we ended up using our alerts data. We have these 4 types of alerts and also the Overture Maps data. And from there, we get the places data. This is points of interest in Nagpur city, and these are geolocated. And we are focusing on hospitals and also schools, because hospitals is health infrastructure, and schools could be also a risk factor for road traffic accidents. Now, for the second step of our methodology, we were talking about cleaning. Cleaning was basically deleting the non-geolocations or stuff like that. We didn't have to do much in that side because it was quite clean, but we needed to see a way in which we can make it more efficient. So that's why we decided to perform a spatial aggregation. And just to introduce this, there are many ways out there to do a spatial aggregation. Some of them are by region, by city, by zip code, and also some indexes like S2. Those are rectangles or so. But we also have this new index that was introduced by Uber, and it's a hexagonal hierarchical spatial index. So what this would allow us to do is that here you can see we can map all of our world, all of our maps with hexagons. And we can do it at different resolutions. So here we see an example of a map, and we are not aggregating those points by zip code, because zip codes are sometimes very different, like they don't have the same shape, but we would be aggregating them by hexagons. And with this, we would be able to create these hexagons, and instead of considering each point separately inside that, we aggregate it and we consider like the count of points inside each one of the hexagons. And this would also allow us to decide which level of resolution do we want. So the library, this is an open source library created by Uber again. would allow us to pick between different resolutions. We are using for this use case resolution level 8, and that would mean that we are, with each hexagon, we are mapping about an area of a bit less than 1 kilometer. But if we wanted to, at some point, consider more areas for each hexagon, we could use level 7 or level 6, and it goes up until level 14, if I'm not wrong. We will not keep talking more about it, but we're just leaving here the full documentation of this spatial aggregation method. And now we can move on with the results. So with that process, we created these interactive dashboards, and we have 3 different insights or 3 different types of dashboard that we created. The first one is the spatial distribution of alerts in Nagpur. And I will show my screen right here. So this is a screenshot, but we can actually get it as an HTML, and at some point we can also get it as a service if we would want to productionalize this. And here we have our data mapped. So for each hexagon, we have the count of alerts. So we see right here, we are focusing our analysis in only Nagpur, because if we would to take a look at the whole map, it would be too much. So now we're going to Nagpur. We see that we have our hexagons. Each one would have its index, and it would have the count of alerts. So here, for example, we can see that between just when we have these 2 national highways and they are crossing, we have the highest number of alerts. So that's about 20,000 alerts. And we also have right here the Central Bazaar Road. This is the road right here. And this was really, having Deshanton in the team that he knows a bit more about the roads in India and stuff was very useful, because I didn't know that this was a road or a street that goes across the market of the city. So of course, that's why we're getting more alerts. It's a very crowded area. And if we move on, we can see some other hexagons with a different count of alerts. And as we go far and we start getting out of the city, we see that the number of alerts start to decrease. So we have not as much alerts, for example, outside of the city. We would have 6 or so. So this is our first insight from this map. We would be getting the highest number of alerts here, but we also wanted to look at, okay, how does this look if we filter by each type of alert? So this map would map all the alerts, but we can also take a look at the pedestrian collision warning. And if we filter only by that type of alert, our map changes only a bit, but we're still getting a lot of that type of alerts. That's 11,000 in these 2 national highways and, of course, the Central Bazaar Road. We can also flatten this map, and that's something pretty nice, because the 3D visualization would allow us to get look at it easier, but we can also look at it in a flat way. And we would see that the highest number of alerts, again, pedestrian collision warning, is happening where our Central Bazaar Road is. Not that much the national highways, because those are national highways for cars, but more when we have a huge market in the city center. So that's something interesting. And also, we had this lane departure warning, and those were by far the most common in our data set. But if we filter by lane departure warning, we see that those are not actually that much in the city center, but those are happening a bit outside the city. So the highest bar would show us what is the occurrence of, or where those are happening more. So this is something interesting. We know that lane departure warning means that they change lanes, but it seems that it's happening more in the outside of the city than in the city center, or in the same way as in the city center. So that's a bit different on the behavior. So that is our first dashboard. And we can move back. That's the first result. the first result that we got, and that would be the spatial distribution of the alerts in Nagpur. And now moving on.
Yes, so the next result that we got was we calculated a risk index based on the alert counts. So the three factors that we take into account is alert counts from the IRASTE data set. Gabriela was able to find a data set which allowed us to get school counts and hospital counts for the city of Nagpur. So we used those three factors and calculated a risk index. And you can see the formula that we used. We assign a weight based on their contribution to the alerts that were being given to us by the IRASTE. And we decided to put different weights to each of the alerts, the least given to school and the highest to the alert count. And we were able to generate a map that you can see. It's similar to what Gabriela just showed. And you'll again see that since the alert count is very focused on that particular intersection where you get the merging traffic from two highways and the Central Bazaar Road, you'll see that the risk index would be the highest there. And like the previous map that you saw, the towers are reflecting towards the alert count as well as the risk index in that area. So using additional information that we did want to, we can basically provide a more a better risk index rather than just using the three values that we have used right now. It's a very simple formula, and it allows us to basically assign a score based on the data that we were able to gather. Also, we have deployed one of the maps to using a Flask application, which everyone can access. I have provided the link in the chat. You can click on it. You'll see a map. The map is about each alert in a particular hexagon that you see right now. So you'll get all the 4 alerts that we focused on. So each alert and how many times it occurs in a particular hexagon. Next slide, please.
Yes.
Okay,
so
you can take over.
And this okay, and this would be our third result. So this is an animation of the trips in Nagpur based in alerts. And for this one right here, I mean, we have only the alerts. We don't have like the actual trajectory of each one of the vehicles, the vehicles. But some of the alerts are happening like with a very small interval. So we can kind of construct those trajectories or those trips with only the alerts. And if we take a look at this video right here, I will make it bigger. This is also something very interesting that the Kepler GL library would allow, these trips animations that with also time considering. So this is not considering only spatial, but also how does this look across the time. So we see that early morning, we are not getting a lot of vehicles, but then as the day starts and the working hours come, we are getting like the highest traffic in the city center of Nagpur. And we are there looking at kind of the trajectories created with the alerts, but we see that again, that intersection between the national highways and the market road is where we're getting the most traffic. So that's definitely something nice to look at, because we see that some vehicles or some trajectories are coming from outside the city and going across the city. But one insight here would be that, okay, maybe we have some buses that really need to go across these national highways. And this can seem a bit like obvious. Those are national highways, they are there to use. But maybe when doing transportation planning or something like that, we can say, okay, maybe some buses can take different times to go out, or maybe go not get inside the city across the markets, but maybe take a different route or something like that. So that's one thing that it could also help looking at this type of visualizations. And of course, like the time factor, we are seeing that most alerts and most like movement for these kind of buses, it's happening between 6 a.m., 7 a.m., and 10 p.m. So we don't have as many alerts in the during like after midnight. This could be also because of the type of buses that we are getting in the data set, but that would be interesting also if those are not buses that, or buses that would work at night too, we are not getting as much alerts. And yes, so this would be our third analysis. And that's all that we have to show right now.
In terms of lessons learned, we have we understand that the problem of road safety is something that needs to be tackled by more than one industry or more than one. It requires collaboration between the IRASTE team as well as, say, for example, hospitals in that area to improve the emergency response time. And the real-time data that we got from IRASTE was a very helpful factor in understanding what could be the potential factors. And of course, just doing a data analysis and giving results is not enough. You need to make a loop and keep improving those results to get something out of it. And this is it from Team 3. Thank you. You can ask any questions if you have.
Very well done.
Yeah, really
go ahead. Go ahead, Dorian.
It astonishes me that 3 teams with practically the same assignment came up with such varying results and very nice visualizations. These are some of the coolest visualizations I've seen in the AI for Good challenges we've done so far. So great job, guys. Really cool.
Yeah, very well done. I think the data visualizations, as Dorian pointed out, it's pretty cool. I don't think it's easy to do these things unless you understand, what the alerts mean and what they are. So I think I really liked all the 3 dashboard, like the filtering of each alert for a spatial distribution and also the risk index. And the animation is really cool. If you want to make a movie of IRASTE, we'll probably have that animation in there. So. Very well done. I think I have to say that all 3 teams, I've shown excellent perspectives. At the end of the day, when what Dishan mentioned is that AI alone, technology alone, is not going to solve this problem. You need a combination of transportation engineers and software developers, AI specialists. And also, at the end of the day, training of the driver, at the lowest level, and also bringing in the hospitals and emergency care. So we are doing all these 4. We call it the 4 E's. I think I mentioned that. So I think you hit the nail on the head. I think we are very impressed with the way Fruit Punch has handled this whole, challenge. It's not about the number of people; it's about the quality of the output. And I think all 3 teams have produced, excellent output. We are very proud. Anbul?
Yeah, no, fantastic team, seriously, right? Because you took Nagpur and you also picked up the Uber, which has a unique, the beauty of having a unique hexagonal ID for the entire world, right? And you also chose level 8, which is a 1 kilometer, that's about 500-meter radius hexagon, right? So really nice. And you have extensively, or you have leveraged the the powers of Kepler GL to the maximum extent possible. Good job on that. Yes. And I know really, Dorian and Jayesh, seriously, hats off to you, and the entire team for from Fruit Punch, right? Because it's really, this is yet another data set, or this is just another data set that you are remotely connected, but you are able to steer the team and all of them to come up with this just shows that the team is capable of the team and your mentor of picking up problem and be able to solve, right? So that's really nice. Congratulations to all the team. Fantastic. Very nice.
Exactly. Yeah, I think if I have to pick the winner, I'll have to give it to all 3 of them.
Thank you for those kind
And actually, I have
words.
to pick 4 winners, including Jayesh and Dorian. For actually, let me correct myself.
Yeah,
I think you have taken this to another level. When we first started, I wasn't really sure what is this AI for good community means, and Jayesh talked to us in detail. Now we really understand, and there are a lot more projects, and then we'd like to get you involved at a really massive scale. I really like the approach of midterm 1, midterm 2. Most challenges is throw the data set and then, let's say come and present. This is the checkpoint where you can steer your course in the right direction, can get feedback. I think Fruit Punch, I think you've done a wonderful job. But the way you handled this challenge and focused on the output results, I think we got good insights. We do have a team of transportation engineers with us. They are already looking into the infrastructure part. But without you knowing all these details, you're able to pick and choose and come back and say, within 10 weeks, I think it's very impressive. I think we should be very proud, Dorian and Jayesh. We need to involve and work with you for the long term. There are a lot of challenges coming up. We can engage with all the engineers that you have, that you train. A lot of things are opening up. So thank you so much.
Awesome.
Yes. Yeah, and thanks to you two, Govind and Anbu, for partnering with us on this challenge, believing in us, because it took some time to get it running, but you believed in this challenge, and then we up and running. But hats off to all these 3 teams. It's less work from our side, Anbu and Govind. It's more the team that has brought up these results. It's their work, hard work. And given that there was this lack of initial participation among the team, there was not enough active members, but still each of the teams managed to steer through and get it done. So it's really fantastic. And it's not like the results are all overlapping with the same team, right? Each one has brought unique insights. So yes, it is really nice to see this challenge coming to an end on a high note. So feels good.
So the question for Dorian and Jayesh, if we need to have these teams present to somebody from IRA State team, will they be willing to do it, the final results?
Well, you have to ask the teams themselves, I'd say. We do I've recorded the final presentation, so we will upload it to YouTube as well. If they can also watch the recording. If they want to reach out and ask personal questions to one of the teams, then that's also possible. If you tell me which you need to talk to, then I can make contact there. That's perfectly fine.
Okay, very good. Yeah.
All right. I think that brings us to the end of the presentation. Thank you, Arasa team, for organizing this challenge with us. Special thank you to Jayesh for pulling the car on this challenge, because it couldn't have done it without you. And most of all, thanks of course to all the participants for all your hard work, blood, sweat, and tears over the last 10 weeks. Please do know that it doesn't go unnoticed, and we appreciate your hard works and efforts very much. I'm really looking forward to putting everything in a blog post and on YouTube to give you guys the credit that you deserve as well. You will receive some peer reviews from me tomorrow or the day after, so I can create your certificates as well. So that's also still coming up. But for now, I think that's it. One final thank you, and I wish you a very fruitful evening.
Yes, great job, everyone.
All right, take care.
Yeah,
thank you so much.
Thank you, guys.
Okay, bye.
Bye.
Good evening.
Bye-bye.
Bye.